Okay, I guess we can start now. Am I audible? Yeah, thank you, Bhaskar. We'll start with brief intro. Meanwhile, other people will also join. So it's already 6. So good evening, everyone. Welcome to the week 10 of problem solving discussion for the course NOC 22 C68 Ground Improvement. It's an NPTEL course which is currently being tutored by Professor Dilip Kumar Bedia, who is from Department of Civil Engineering, IIT Kharagpur. Myself, Rituraj Sujawat, I am Prime Minister's Research Fellow in Department of Earthquake Engineering from IIT Roorkee. So those who are coming to these videos for the first time, let me tell you, this 1 hour session will be including the interactive session with the NPTEL learners of this course. We'll be discussing some of the sample problems which will be helping you in solving the assignment questions for this week. Also, if you are having any doubts regarding any part of the lectures which is covered in this week or previous weeks, we can discuss about that also. And any non-technical query or related to this course, we can discuss that also. So this week we have covered about the soil nailing. So basically the principle of the soil nailing is that whenever we'll be having some unstabilized ground here, or we'll be having some excavation, and if you want to prevent the falling of the ground from failing, so in that case we usually go for the nailing or anchoring. So the difference between nailing and anchoring is, the nailing we will introduce directly into the ground, and anchoring will be having some grout material also to prevent that. So this is the this uh, week we will cover about the nailing part. So some of the basic application of the nailing is, like whenever we want to introduce a retaining wall to prevent the failing of the ground from the lateral pressure, we used to go for the nailing. One second. Yeah, fine. And also to prevent the failure of the slopes, and if you want to stabilize the slope, we used to go for the soil nailing. If we are having some expansive soil beneath the any structure and we want to prevent that soil from further expansion, we used to go for the nailing. So here you can see that we have uh, inserted a slab and we are preventing its failure from the nailing. And also in the concrete dam, since we know in the concrete gravity dam, we used to have the uplift pressure at the bottom of the dam. So this uplift pressure can create an upward force on the dam structure, which can make it unstabilized. So in that case we are introducing nailing here so that this dam won't fail. So this is another concrete dam stabilization application where we are going for the nailing. So let's see how in the field or on the real side we are introducing the nails in the ground. So you can see first we are making some excavation of the holes in the ground, and then we are inserting some bars in that excavation holes. Then we are placing some plate. Before placing the plate we had applied some shotcrete also. So that's how like you will go step by step. So once first you will excavate some area, you will nail for the upper part. Then when the ground corresponding to that part will become stabilized, you will nail the below part, and this is how you will proceed in stabilizing the ground through the nailing application. So this is a brief uh, overview about the nailing, and then we'll be proceeding for the questions related to the nailing. So let's start with that. So the first question is, while going through the lectures, you would have come across the various principles associated with the failure of the nailing. So for those failure principle, we used to design our nails. So among one of them, this is one of the failure mode. So corresponding to this failure mode, please choose the option, whether it's nail soil pull out failure, whether it's ball grout pull out failure, whether it's nail tensile failure, or it's all of the above. Let's wait for 2 minutes so you can solve it, and or else like definitely I'll gonna to explain that. I guess maybe due to festival we are having less viewers now. But yeah, these sessions are scheduled at Tuesday only. Yeah, thank you, Bhaskar, for the answer. Let's check with that. Yeah, so it's nail tensile failure. So if we can see the other failure modes, so basically in the nail tensile failure, you can see the tension in the nails. So basically this nail is made up of some steel material or some other material, fiber material, which is included in the ground. So due to the lateral pressure, the tensile force in this nails will keep on increasing, and there will be a instant where this nails won't be able to bear the pressure from this lateral force, and therefore these nails will fail in the tension. And these are some of the other modes of failures in the nails. So first is the nail soil pull out failure. So you can see that the soil around the nail or around the grout, like the interfacial interaction between the soil and the nail is lost due to this failure surface, and therefore we are having the failure of the nails. Another part is that we are having the grout pull-out failure. So the interface between the nail and the grout is failing. So therefore, this nail won't be able to bear further horizontal load. And then we are having the nail bending or shear failure. So if we are having a high vertical force uh, here, so this vertical force basically leads to the flexural failure of the nails, and therefore we'll be having the failure of the nails in bending or the shear failure. So this is corresponding to the beam problem which we used to deal in the structure mechanics. So therefore we can see that due to the high vertical force or the moments, this beam or these nails are failing in the shear or the moment. Let's proceed for our second question. So this is basically about the type of the soil in which we basically go for the nails. So the favorable geomaterial for soil nailing installation is are A. Steep to hard fine grained soil. B. Very soft fine grained soils. C. Poorly graded cohesionless soil. And D. All of the above. Let's wait for 1 2 minutes and then I'll show you the answer. Yeah, so the answer is A. We basically go for the nailing in the geomaterial, which is basically the steep to hard fine grained soil only. Because in the soft fine grained soil, there won't be that much interfacial force between the nail and the soil, and the poorly graded and cohesionless soil will also be subjected to the same problem. So here in the soft fine grain soils, we won't be having the interfacial force that much to prevent the failure of the soil. But in the poorly graded cohesionless soil, the interaction between the soil and the nail will be less. So in the B part, though there will be interaction, but the force required to prevent the failure of the soil will be less. But C, we won't be having the interaction itself. So the only part is like if we are having the steep to hard fine grained soil, then we can go for the soil nailing. So yeah, Any query regarding this? Okay, let's move to the next question. So this is a typical diagram at a site where we used to install the nails, and this is the slab or the retaining wall which is basically preventing the failure of the surface, and we are including the nails to stabilize this wall. So there are different zones of the soil where we have divided. So X, Y, Z. So you need to show what X basically represent here. What type of zone it is, whether it's stable zone, active zone, passive zone, or none of the above. So it's similar to the lateral earth wall pressure problem. So what type of zone it is? So if you may want to see, so Bhaskar, yeah, it's basically the active zone. So I'll show you the other zones also. So this part of the soil just beneath the wall, we used to call it as the active zone, because since here we are, like, if the nails won't be there, so there will be active earth pressure, and here due to the confinement we'll be having the passive pressure, and these are the failure surfaces, and below the failure surfaces, like we can see, like we'll be having the stable zone. So if there won't be enough toe resistance, like here, so this will be the potential failure surface, and if there will be sufficient toe resistance, so this will be the failure surface. So we'll be having the stable zone, and this is the active zone X, and Y will be the passive zone. Any query in this? Okay, so let's move to our numerical part. So question number 4 to 7 will be based on this comprehension only. So basically, for an excavation in silty sand, a permanent soil nail was proposed. The depth of excavation is 9 meter and the wall is vertical and the slope of the topsoil surface is 10 degree. Cohesion, friction angle and the unit weight of the silty sand are respectively 2 kPa, 32 degree and 19 kilonewton per meter cube. The global factor of safety is given as 1.5 and the factor of safety again pull out is 2. The diameter of the drill hole is 150 mm. The required global factor of safety is 1.5. The factor of safety against pullout is 2. The diameter of drill hole is 150 mm and the ultimate bond strength between nail and the soil is 125 kPa. We are assuming nails are placed at a spacing of 1.5 meter in vertical and the horizontal direction. So basically you need to find out first the normalized pull-out resistance. So you can read question by yourself also. Then I'll explain the first part. So let me explain you the problem. One second. So the problem is we are having an soil nail hole here. There is a silty sand here, if you can see. The properties of the silty sand is given as cohesion is 2 kPa, phi is 32 degree, gamma is 19 kilonewton per meter cube, the slope of the top soil surface here is given as 20 degree, sorry it's 10 degree. So this angle is given as 10 degree. The factor of safety for the whole global failure is given as 1.5 and factor of safety against pull out is given as 2. They are introducing a nail here. The diameter of which is given as diameter of the hole, it's not the diameter of the nail. So diameter of the hole is given as where it is, yeah, 150 mm, and the bond strength between the nail and the soil. So this we'll be introducing some nail here in this hole. So this corresponding strength between the nail and the soil, we can say it's given as 125 kPa. So first we need to find out the normalized pull-out resistance. So anyone with the answer? Yeah. So the correct answer is 0.219. How we come with that? So the pull-out resistance is basically given as toe ultimate diameter of the hole, factor of safety and pull-out. Then we are having the gamma of the sand, spacing in horizontal direction and spacing in the vertical direction. So toe ultimate, I guess it's given as 125, diameter is 150 mm, so it's 1.15 meter. Factor of safety and pull out is given as 2, gamma is 19, spacing in horizontal and vertical direction is given as 1.5 and 1.5. So let me calculate for you. Spacing in horizontal and vertical direction, 120 into 125 into 0.15, answer divided by 2 into 19 into 1.5 into 1.5. So it's 0.21. Any query in this? Yeah, so basically it's the relation toe ultimate into diameter of the hole divided by the factor of safety and pull out. So since we are asked to calculate the normalized pull out resistance, so the this pull out resistance is basically normalized with the spacing of horizontal and vertical direction and with the gamma, and this is your pull out resistance, tau u into dh. So the answer is 0.219. Let's move to the next question. So next you need to calculate the normalized cohesion. So basically all these parameters which we are calculating, it used to help us in designing the required nail dimensions or the characteristic strength or the what we can say the material strength which is required to be inserted into the ground, so that if we know beforehand what is the lateral pressure available or what the lateral pressure is being applied by the soil to the wall, so how I can prevent that wall further from failure. So that failure, if I want to prevent from the nail, so I need to design the dimensions and the strength I can't design, but I need to design the dimension and whatever material strength or the material is available of the required strength in the market, we are going to adjust the dimension of the nail or the diameter of the nail according to that. So yeah, so for that these all parameters are being calculated. The another parameter is the normalized cohesion. So how we can calculate the normalized cohesion? Let's wait for 1 minute, then I'll solve. So we have calculated the normalized pull-out resistance in the previous question. Here we are going to calculate what will be the normalized cohesion available with us. So the given cohesion is 2 kPa. So like you need to calculate, you need to basically normalize it. So normalization is basically like in the vague terms, I'm saying that it's basically we are making it as a dimensionless. So the only purpose of normalization is not to make it as a dimensionless, but like if you want to solve the question, so how to come up with the formula. So this is 2 kPa, how you are going to normalize it. So yeah, let's solve this. So the given cohesion is available with us is 2 kPa. kPa is basically kilonewton per meter square. So I need to normalize it. So let's call C normalizer C bar, and usually for the nail design we used to normalize it with the factor gamma into h. So C is 2 kilonewton per meter square. H is the height of the wall available with us. Gamma is the unit weight, so 19 kilonewton per meter cube, into H is the, so depth of excavation given available with us is 9 meter. So 9 into 19 into meter. So 2 divided by 19 into 9 is basically 0.01169. So if you approximate it, it will be 0.117. So C will be the answer. So the length correction factor for soil cohesion is, next question available with us. Any doubt in previous question? Sorry, I forgot to ask. Fifth question. Okay, thanks. So sixth question we are having. Basically, we are correcting the factor for the soil cohesion. So how? What is the factor? So basically the whole cohesive strength is not available throughout the soil. So we are modifying that particular cohesion on the basis of the length. So there is an empirical formula which is being discussed in the NPTEL lectures by the Professor Bedia. So in that we have discussed. So please come up with the length correction factor for that particular cohesion. So yeah, if you remember that empirical formula, it's only 10 seconds calculation. Okay, no problem with that. Let me give you. So the length correction factor uh, basically given by C corrected. Oh, yeah. So the length correction factor for soil cohesion. So it's given by -4 the cohesion given, or like it's the normalized cohesion which we have calculated plus 1.09. So -4. See, we know we have calculated 0.0017 plus 1.09. So if we calculate this, we are having 1.04. So the correct answer is B. The last question for this comprehension is, so if the corrected normalized nail force for each soil nail is 0.30, then the maximum design nail force for each nail is. So the normalized nail force for each nail is 0.30. For each nail, the normalized nail force is given. Now you need to calculate the design nail force for each nail only. Like for single nail, the normalized force is 0.30. So the maximum design force for single nail will be how much? So if you remember the fourth question, like this is how we have normalized. So here this thing is given, then you need to calculate the normalized nail force. So the factor by which we have normalized it earlier, it's basically the maximum design nail force. So in this factor, in this corrected normalized nail force, the factor of safety is already included. So don't use that. You only need to calculate the maximum design nail force. So it's, let me calculate. Okay, let's wait for 1 more minute and then I'll show you. So the maximum design nail force. So for each corrected nail force, each corrected normalized nail force is given as 0.30. So the corrected normalized nail force for each nail is given as 0.30. So now you need to calculate the design nail force for each nail. So maximum design nail force. So it's basically given by tau normalized into gamma into h into spacing in horizontal direction and spacing in the vertical direction. So tau is given as 0.3, gamma you know it's 19, h is given you 9, spacing in horizontal 1.5 and it's 1.5. So the answer is 115.4. So the maximum design nail force is 115.4. Any query in this comprehension? So it's a similar problem we used to solve in the RCC. So where we used to have some strength in shear or in the interface friction strength available with us. So we need to basically calculate the length of the rebar or how much is the force is being induced in the bar. So the same, like the similar approach we are using here also while calculating the nail. Only thing is in place of the rebar we are having the nail, and in place of the concrete we are having the soil here. So let's move to the next set of question. So this is basically the analysis problem. So we are having the proposed brace excavation at a site with the pressure diagram given here. So this is basically the pressure diagram of the soil or the lateral pressure of the soil. So how the pressure of the soil is varying means it's not exactly like that, but for the calculation of the forces in the nails and the soil in the literatures, it's being said that this is how we will vary the pressure diagram for calculation of the forces in the nails. So the studs are spaced longitudinally at 4 meter center to center, and the sheet piles are pinned or hinged at strut levels B and C. So your wall basically this walls to prevent the lateral pressure from the soil is being prevented by the nails, and these nails, among these four nails, the nail B and the nail C is pinned or hinged. So now you need to calculate. Also the properties of the soil is also given. The gamma is 17 kilonewton per meter cube, and the what we can say shear strength is 100 kPa. So this is your pressure diagram. Now first you need to find out how much will be the load on strut A. So due to this soil pressure, how much will be the force induced in the strut A? So the options are this. So I think I should show you the diagram only. So basically you need to find out how much will be the force in the A. So let's calculate it. Try it for 2-3 minutes and then I'll solve it. Pressure diagram is given. This is basically, you can consider this wall as a beam, and these forces here A and B, you can treat it as a reaction. So now basically you need to calculate the, what we can say, reaction at A and the reaction at B, and also it's given like it's a hinge here. So how we used to solve it in the mechanics or the solid mechanics, in the similar approach we can solve it here also. I guess there was some connection issue from my end. Mm. Am I audible? Yeah. Ashish Bhaskar, can you please? Okay, thank you. And my slides are also visible, right? Okay, cool. So let's solve this question. So we basically need to calculate the load on a static. So the correct answer is 331.5. So yeah, only A and B are given. So it, this is basically your soil wall. Here the nail is placed at the position at A, and then we are having the position of the nail at B. So the pressure diagram is given. So it's basically here, here, and here. So the length is 0.25 h. So h is 4 meter. Yeah, h is 12 meter. Sorry. So h is 12 meter. So 0.25 is 3 meter. So this is 3 meter. Since only up to forces in A and B are asked, so we'll like in the next session also you need to calculate the load on the stud B only. So I'm considering only this much pressure diagram for the calculation. So this is your A and B. So you can say the force here acting is A and force here is B. So basically these are the reaction. I should not say force. So reaction at A, reaction at B. So how whatever will be the reaction that corresponding to that will be having the force. So this is 3 meter here. So if we can see we are having this is 1.5 meter here and this is 3 meter. So let me draw the diagram again. Wait a second. So here you are having this much length and this is your 1.5 meter. So here this is 3 meter and this is 1.5 meter, right? So the pressure diagram is here. So now the one key point here it's given as like this point is basically the hinge. So we know from the property of the hinge like about the hinge or at the pin end we can basically take the moment as 0. So if this is your end A, this is your end B, so the moment about B can be calculated as, so the lateral force from this part and this part and the reaction provided by A. So sigma MB is basically 0. So if we calculate the moment about B, so the force from this. Also the width of this tributary diagram is given as 0.25 gamma h. Yeah. So this 0.25 gamma h, if we can calculate, gamma is given as 17 and height is 12. So 0.25 into 12 is basically 3 into 17 is 51. So this length is gamma is kilonewton per meter cube, so it's kPa. So the force from this part of the pressure diagram will be half into so sigma mb is 0. Force from this pressure diagram is half into 51 into height is 3, and also we need to consider the like this is not a 1D problem, this is 2D problem. So inside this, so if you take basically the cross section, so yeah, if you take a cross section here, so for the A section, or like let me tell it as a XX section. So if you see it from the top view, where should I draw? Let me draw here. So the XX section basically like here is your one strut, here is your one strut. Like let me draw this. Here is your one strut, here is your one strut, and the distance between them is given as 4 meter. So half into 51 into 3 will give you the this area, and then you need to multiply it with the inside the plane also, so that will be the 4 meter. And then we need to calculate the lever arm. So lever arm for this triangle is 3 plus 1/3 of third. Then we need to calculate the from here, the force from here. So this is basically the rectangle. The length is 1.5 with this 51. Inside plane depth is 4 meter, and the lever arm here is 1.5 divided by 2. So basically we are considering from here, and since the nail B, like this nail is located at the B only, so there won't be any component of this while calculating the moment, but we'll be having the component of the nail A. So that will be the, like this will be having the reaction at A. So this is RA, this triangular force is this rectangular force is this, and then we'll be having the RA. So reaction at A will be given as -3 into RA. So this will be the overall moment about B. So if we can calculate 3RA, so 51 into 3 into 4 into 0.5 into 3 plus 1. Did I make mistake here? 51 into 3 into 4 into 0.5 into, yeah, sorry, this is 1.5. Basically this length 1.5 and this length, like the force will be acting here. So 765 plus 1.5 into 51 into 4 into 1.5 divided by 229.5. So if I'll calculate the RA, so 765 plus 229.5 divided by 3. So yeah, it's 331.5 kilometer. So we'll be having the A as the option. So this reaction at A will be equal to the force at A. So force at A is equal to reaction at A, and it is equal to 331.5 kilometer. So yeah, any query in this? It's basic mechanics problem. We are having the pressure diagram here up to B. Like this pressure from the soil is being registered by the two nails up to the point B. So since at B it's given as the nail B is hinged, so we have taken advantage of this part, and we made it the moment about B as 0, and then we done the whole, like it's simple mechanics problem. Then we are having the force component from the this nail A, and this triangular part force and this rectangular part force. So let's move to the next part. So now you need to calculate the load in the stud B. So I guess we are short of time, so let me calculate this for you. So it's similar thing, like basically, let me draw diagram again. This is the nail, so you are having reaction at A, you are having reaction at B. This is basically resisting the pressure from the soil, 1.5 meter, this is 3 meter, this is 3 meter, this is 1.5 meter. So you have already calculated the reaction at A. So like we can take the advantage of equilibrium, and we know sigma fx equals to 0. So RA plus RB is equals to the force from here. So the force from here is like this is We have calculated it's 51 kPa. So half into 3 into 51 into 4 plus 5 1.5 into 51 into 4. Yeah, so I guess yeah, that's it. RA we have already calculated C31.5 earlier. So RB, so 0.5 into 3 into 51 into 4 plus 1.5 into 51 into 4, it's basically 612. So if I evaluated RB minus 331.5, did I do anything wrong? 1.5 51 into 4 half into 3, reaction at A. So 0.5 into 3 into 51 into 4 plus 1.5 into 51 into 4. So this is 612. Then yeah, I guess RB 612 minus 331.5. It's 280.5 kilometer. Guys, 1 second. I guess the options I have written it wrong. One second, guys.